better. All right, of the different molecules, linear, angular, pyramidal, and tetrahedral, and we had a look at the repulsion between electron pairs, lone pairs, and bonding pairs, bonding, lone pair. All right. And we explained the shape of the molecules. Now, we are still busy with bonding in general. I did mention water, that is a polar molecule. If you look in your textbooks on page 31, they discuss the different structures and the angle on the left-hand column in the block at the top. On the right-hand side, they discuss the water molecule. It has two lone pairs. So the structure of water is similar as it is shown in the table. The structure explains why water was attracted to the charged ruler. We said water is a polar molecule. I said to you yesterday, why is water polar? Because if we look at the bond of oxygen and hydrogen, if that's the hydrogen, oxygen, we have the electron pair repulsion pushing down the hydrogens at an angle on the one side of the molecule. Yes. But if you go and look at why is oxygen the slight negative side and why is hydrogen the slight positive side, then it has to do with the oxygen molecule has got two lone pairs of electrons. They are negative. So that side of the oxygen molecule is going to be negative. And then I said to you the other reason is because of the attractive force of the nuclei on the shared pair of electrons. And I said to you that, I must rub that one out. Yeah, okay. That the oxygen atom has a stronger force of attraction on the shared electrons than what the hydrogen nucleus does. Just very simple, the oxygen has a positive charge of 8 protons, where hydrogen only 1. So plus 8 is going to attract the negative stronger than plus 1 will. And this together makes that the water is polar. And the fact that water is polar then explains a lot of the behavior of water molecules, the high melting and boiling points, the expansion when it freezes, etc. Okay. The next type of bond that we must go and have a look at is the ionic bond. Just want to see something before I get there. Okay. Yeah, I've got another note for you because we need to know about the forces between particles. It's just they've written it just to make it look like the others. Verstaan jy? But it's not. Technically, we write it H2O. But it's not wrong. I think they've just done it because it fits into the pattern of the other non-metal hydrides. Okay. All right. I've handed out a note, and it's got to do with the forces between particles. Now, I haven't done ionic bonding in detail. We don't do much more in terms of ionic bonding than what we've had. For example, if I want to look at the bonding between sodium and chlorine to form sodium chloride, then I have one sodium atom with one electron in its outer shell. All right, and I have one chlorine atom with 7 electrons in its outer shell, 4, 5, 6, 7, and we find that the sodium, because it is the metal, is going to give its electron to chlorine, and we are going to get a positive ion and a negative ion. What force lies there between positive and negative ions? Coulomb or electrostatic forces. And from what we've done previously, we consider these forces to be, relatively speaking, strong. If I had a look at something like magnesium oxide, all right, then I will have HGO. I will have a magnesium atom, and I will have an oxygen atom. Oxygen has 6 electrons. Magnesium has 2. And we are going to find that the magnesium is going to give its electrons to the chlorine, the oxygen, sorry. And we are going to get +2, -2. That's exactly what I want to show you now. What forces are between the magnesium and the oxygen ions? Electrostatic forces. But can you see that the charge is bigger? If you had to say which one has the higher boiling point? Magnesium oxide. It's got stronger forces holding the particles together. Do you understand? There's another factor that will influence the force between the particles. Sodium and chlorine they all lie in group 1, 2, 3. The third period, and oxygen lies in the second period. What will make the forces even stronger, because oxygen lies in the second period, it's got 1 shell less. So the particles can get closer together. So the forces act over a shorter distance. It's like having 2 magnets. If they're far away, the force is weak. But if I get them close, the force is strong. And that also contributes to this one having a higher melting and boiling point. No, both will be higher, because the forces that have to be overcome is greater. Okay. Do you understand this? Okay. Now, in the notes that I've handed out, there we're going to have a look at the forces between particles. Now, when I talk about particles, they can be atoms, they can be ions, and they can be molecules. Why are metals strong? Positive atomic rests in a sea of delocalized electrons. What type of forces hold them together? Electrostatic, Coulomb forces. Do you understand? All right. No, ions. There are ions in metallic bonds, yes. Because the positive atomic rests have lost their outer shell electrons. They are delocalized. So we have resulting ions. Technically, metals are crystalline. And the particles are ions and electrons. Positive ions and electrons. All right. Okay. Now, in the note that I've given you, the first one is forces between ions. That is usually the easiest to understand. Because we have charged particles, the forces that hold these particles together are strong Coulomb forces. If the charge is bigger, like we've just seen in the example, the forces are stronger. Right. The problem comes in when we have, well, atoms and molecules especially. If I have water, I have water, oxygen and hydrogen, and I have another water molecule, and I have the hydrogens on it, and I have another water molecule with the corresponding hydrogens on them. What forces are there between these particles? When we did the characteristics of molecular substances, soft solids, low melting and boiling points, weak forces. Yes, the forces between molecules are weak, and the name of the forces are van der Waals forces. All right? It's the name of the forces. But it's never as very simple as that. Van der Waals forces actually incorporate a couple of things. All right? So if you're going to have a look at the diagrams that I've given you, there's an A and there's a B part. A, London or dispersion forces. Now, they are both intermolecular, between molecules. What does intramolecular mean? Inside. Intramolecular, what forces do I have? Covalent bonds. You understand? The forces holding the hydrogens and the oxygens are covalent bonds. All right? Intramolecular, but inter is between. The inter-Cape bus goes between Cape Town and Windhoek. All right? So it's between. Intermolecular forces are these weak van der Waals forces. Now, the two that you must know of, they talk about London or dispersion forces. And the other one is so-called hydrogen bonds, but it's not a chemical bond. Yeah, just hang on. The hydrogen bond is not a chemical bond. It's an intermolecular force. All right? Now, if I have a molecule, let's say I have chlorine, it's a gas. Diatomic, so two chlorine atoms are covalently bonded. And they're giving me a chlorine molecule. Are you with me? Okay. I have lots of chlorine molecules. What forces do we get between them? Weak van der Waals forces. All right. Now, what happens is, when we talk about London or dispersion forces, remember these particles have energy and they bump into each other. Now, if this molecule would, for example, bump into that one, for the split second that they make contact, the electrons are able to be pushed away from each other. And they will push the electrons of the one to the other side, and we say just for a moment, it makes the molecule slightly polar. All right. So the force at that point of contact is an induced dipole, induced dipole. All right. It wasn't a polar molecule, but just when they connected, because the electrons can be pushed around, we get a slight positive and a slight negative side to the molecule. And when we have a slight positive and a negative side, it's a dipole. So this is an induced dipole. Now, this type of forces are known as London or dispersion forces. You don't have to remember about the induced dipole. I just used to explain it. Okay? So between my molecular substances, diatomic molecules, most of them are gases. Bromine's a liquid, iodine's a solid, but it easily undergoes sublimation. So are the forces strong holding them together? No. What forces do we have between those molecules? We have London or dispersion forces. They are weak. Then we get special van der Waals forces, and that is what we get between water molecules. If I go back to my water molecules, remember we said the water molecules have a slight negative charge, all right, there, and a slight positive charge. So, negative and positive will attract. Okay? And these forces are definitely going to be stronger than what they would be between two consecutive, no, I must go the other way, iodine molecules. Do you understand? Because the iodine molecule, it doesn't have a slight positive or a slight negative side. Now, those forces between water molecules that arise as a result of the polarity of the water molecule, we call those forces hydrogen bonds. But technically they are not chemical bonds. But this is why water that is a polar liquid tends to have higher melting and boiling points than other molecular liquids. All right. Actually, most of the other molecular substances are gases. Carbon dioxide, sulfur dioxide, hydrogen sulfide, If you can think of a molecular gas or a molecular substance, it is in the form of a gas. Why? Because the forces between the particles are very weak. There are a couple of exceptions. One of them is water. Now, when do we get hydrogen bonds? Usually, when hydrogen bonds onto oxygen, nitrogen, or fluorine. There is another added factor. The molecule mustn't be symmetrical. Because if it's symmetrical, then the charge distribution is equal. All right, and we don't have the resulting polarity. So, yes, ammonium, but ammonia will be slightly polar. All right. Do you follow? So when do we get hydrogen bonds between molecules? Usually molecules made up when hydrogen bonds onto oxygen, hydrogen bonds onto nitrogen, and hydrogen bonds onto fluorine. Now we don't really work with the hydrogen nitrides. It's a chemistry that sort of goes on its own. But hydrogen fluoride, we can work with that one. And hydrogen fluoride will probably be polar. Why? Because we have hydrogen and we have fluorine sharing electrons, but fluorine has a very strong force of attraction on the electron pair that they share. Now, no, one bond in place, one bond in place, okay. We refer to the electronegativity of an element. Electronegativity is an indication of the attractive force on a shared pair of electrons. And when you look at the periodic table, fluorine is the most electronegative element. So electronegativities increase from left to right and decrease from top to bottom. So, when hydrogen bonds onto nitrogen, oxygen, fluorine, they are of the most electronegative elements. We find that are the electrons shared equally? Nope. They all attract the electrons away from hydrogen, making the molecule slightly more negative and slightly more positive. In water, it's very extreme because of the lone pairs and the angular shape of water. All right. So hydrogen bonds are stronger intermolecular forces. So if you look at the notes, I try to show it with diagrams. London or dispersion forces, they lie between molecules. And the forces are, relatively speaking, weak. We call them London or dispersion forces. You don't need, yes, they are collectively van der Waals forces. But if they want to go, if they ask you what's the difference between, why does water have a higher boiling point than hydrogen chloride? Then you have to go and explain about the forces, all right? Hydrogen bonds, special van der Waals forces. The hydrogen bond lies between molecules. Strictly speaking, it is not a chemical bond. Okay. That about the forces between particles. Now, ionic bonds. There's not much I want to say there. People, you should be able to do the ionic bonds of the first 20 elements, metals with non-metals. That hasn't changed. Nothing has changed from what you've done it from grade 8. Okay? If you don't understand it, you must go and try and do them, and then you must come to me and you must ask. Okay? But you should be able to do the ionic bonding. It's not difficult. Then there in your books on page 32, table 2.14, properties of ionic and covalent compounds. The ionic compounds, they say, are crystalline solids. Crystals are hard, brittle solids. The second point, when they are melted or dissolved, you can write in, they will conduct electricity. They have high melting points, high boiling points. They have high heats of fusion and vaporization. Janus, why? I suggest you come and sit on the side of the pillar. Jy gaan breinskade opdoen, regtig. Nee, jy sit en kyk in haar oë. Jy doen. Want jy sit en praat. Gaan sit daar, want jy kan nie my vraag antwoord nie. Move. Ek gaan nou kyk. Skuif, broer. Waar is jou boeke? Ek kyk dat jy dit inskryf, maar hy het dit nie ingeskryf nie. Seriously? Oh, how depressing. Hy moet pas op, hy sal dalk nie vir sy vrou eendag kan sorg nie. Okay, people, we said the ionic solids, hard brittle solids, high melting and boiling points, all right? They have high heats of, latent heats of fusion and latent heats of vaporization. What's that? Fusion is melting. It's the energy needed to separate the particles so that they can melt, so that they can slide over one another. And vaporization is the energy needed to overcome the attractive forces so that the particles can move freely as a gas. It connects up with high melting and boiling points. All right. Then the covalent compounds, most of them are liquids or gases. If they are solids, like iodine, they usually undergo sublimation. Who knows what mothballs are? What type of bond would be between those particles? Or what force holds the particles together is probably a better word. Weak van der Waals forces, they undergo sublimation. Those air fresheners that they put in the toilets, the little block in the cellophane paper, it's going to be molecular because it undergoes sublimation. There's usually an exception or so, but I don't know of an exception. All right. Yes, the naphthalene is bonded covalently. The forces between the molecules are weak van der Waals forces. That is why they can undergo sublimation. And then one difference then with the molecular compounds, they do not have an ionic charge. If there is no charge, can they conduct electricity? No, because current is moving charge. No charges that can move, then it cannot conduct in any state. Why can't salts conduct in the solid state? Sodium chloride salt, it doesn't conduct electricity when it's solid. Why not? In other words, the particles are held in a fixed position. Can they move? Only the vibration, according to the theory, but they can't move. And for you to be able to, or a substance to be able to conduct electricity, there must be charges that can move. But when it's liquid, the attractive forces have partially been overcome. Now the ions can slide over one another. You with me?
Now, can you ever get a pure liquid of salt?
A liquid of salt, yes.
Yes.
Yes. Yes. They just have very high melting and boiling points. For example, aluminium oxide, I think the melting point is something like 1,500 degrees or something like that. Okay. That is why they use salt in these new type of salt generators. It's the one that they have near Uppington. It is, I think there's salt in it, and it from the sun, yes, and the salt has a very high melting point, so when the salt becomes molten, there's lots of energy in it, and it can give this heat to boil water, which makes steam, which drives a turbine, which generates electricity. Yeah, just more or less, yeah. Yes, you can burn, because it will be extremely hot. All right, you could go to them, if they had to work on them, they would go at night. or they would disable the mirrors. But it's probably just easier to go at night. Okay. All right. Ionic crystals, they're on page 33. Just know, very strong. What forces hold them together? Coulomb forces. The orderly arrangement is a crystal lattice. Okay, and now one of those strange things in your syllabus, we don't go into the shapes of the crystals. That becomes a separate part in chemistry. You can recognize which substance you have on the shape of the crystals that have been formed. So crystalline shape is unique for different substances. Now, in sodium chloride, they specifically want you to know the arrangement of the particles in the sodium chloride crystal lattice. We say sodium chloride forms a cubic structure, close-packed cubic structure. In each sodium chloride crystal, the pattern that is repeated is one sodium ion is surrounded in 3 dimensions, so in the front, in the back, to the left, to the right, to the top, to the bottom, by 6 chloride ions. And each chloride ion is surrounded in 3 dimensions with 6 sodium ions to form this cubic structure of the crystal lattice. Yes, that part there. That is the only one you need to know of. They have asked this in the external exam. I don't know why they go and just refer to one particular crystal and its shape. I think maybe just to sort of give you the notice that they do have unique shapes and arrangements to their lattice. All right. So please take note, sodium chloride with the arrangement of 6 sodium ions surrounded by, or surrounding each chloride ion, and around each sodium we have 6 chlorides in 3 dimensions. It's impossible to draw because I can't go in front and back. But you can, if you go on YouTube, you will find sometimes the molecular shapes that they build with models, and you can get that. When I break a sodium chloride crystal, it will break along a specific plane. And that is why it will always, whether I have a big block of salt like this in its crystalline structure, or I have a little grain of salt that I can put over my food, if you looked at it under a microscope, it would have the same shape, the crystal. Okay. Yes, yes, it goes along a face. All right.
So that is why when you cut it at the ends to that point, it kind of, you can chop it only in the middle and it will end up split.
Yeah. If I have, well, water, I've got H2O. I know specifically I have 3 atoms, 2 hydrogens and 1 oxygen. But if I have sodium chloride, how many do I have? In a crystal lattice, there can be billions. And in a smaller one, there can be millions. And in an even smaller one, there will be thousands. Do you understand? The formula just gives me the ratio in which they occur. It doesn't give me the number of ions that I have in the salt that I shake. If I could pick up a little crystal, there's not only 2 ions in that one. There are millions. Okay. So that is another thing with the formula of salts. It just gives me the ratio in which the elements occur to each other. It does not give you, like in a molecule, I've got exactly 2 hydrogens and 1 oxygen. It can vary in my salts. Okay. If I have a tiny little crystal, I'll have less ions than if I had a big block of crystal. Okay. That is there on page 33. And then they've got electronegativity. They say it is the name given to the tendency of elements. It's actually the nucleus of an element to attract electrons. Elements such as sodium have low electronegativities. What does that mean if something has a low electronegativity? Does it have a strong force of attraction on its electrons? No. What type of ions do metals form? Positive or negative? Why? Because they lose electrons. Why do they lose electrons? They have low electronegativities. Non-metals have higher electronegativities. That's why they gain them. Do you understand? If you want to go technically into bonding, then we get sharing of electrons when the electronegativity difference lies between two parameters. And if the electronegativity goes beyond those two, the difference, then we get a loss and a gain of electrons. That's when we get the ionic bond. All right, because they don't share them equally. The one takes it away from the other because it's got a higher electronegativity. Okay, yeah, they are. All right. The electronegativity on the periodic table, just very simply, if you remember fluorine is the most electronegative element, then the electronegativity becomes less from left to right, and it will decrease from top to bottom. What? There's nothing to explain. I said to you, fluorine is the most electronegative. So electronegativity increases. Oh, I did it to decrease. Ah. Okay, I'm with you now. Okay. No. Still the wrong way around. Seriously? There, I want to do that. Okay, Josh, that's all right. Because fluorine is the most electronegative. It's some of the stupid stuff that person remembers. It's got a value of 4. All right. The other elements are all less electronegative. Oh, this one is also the wrong way around. Seriously. Yeah, must go like that. Yes, it decreases. Bigger than and smaller than. Okay. This is bigger than. The metals have low electronegativity, and it decreases as you go down, because as we go down, then the electronegativity difference will also decrease. Sal ons nog aangaan? Okay, one more thing. The coordinate bond. A coordinate bond, we said both the shared electrons come from one partner only. And one example was ammonia. Okay, there and there and there and there. So this is NH3. It can gain a proton, and where will the proton go? There, making NH4. The first question says, how many protons and neutrons are there in the nuclei of the following isotopes? Iron, 5626. Iron is 56. 56. 26 protons. 56 minus 26 is going to equal 30 neutrons. And because it's and we need to know protons, neutrons. Okay, they don't ask anything about electrons. If the question asked anything about electrons, it would equal the number of electrons, the number of protons. Eh? All right? If the iron had a charge, positive, then that would be an indication of either electrons lost or electrons gained. All right. The next one was uranium. Now uranium is uranium-235, and it has 92, the atomic number. So it will have 92 protons. Yes, and 235 minus 92 would equal the number of 143 neutrons. Once again, if they asked for the number of electrons, it would equal the number of protons because we have a neutral element. Yes, yes, it'll, for example, if I had that, then the number of electrons will not be equal. Plus 2 means it has lost 2 electrons. Yeah, so it would be 24 electrons. Nah? Okay. And if it was negative, it would mean it had gained electrons. Then the next one is uranium-238. Still 92 protons, but the isotope is 238. So 92 protons, because it's the same element as there. And the number of neutrons is going to equal 238 minus 92. So it is equal to 4. Is it 6? Yes, 6 neutrons. All right. Any questions there? There shouldn't be problems. Right, then. The next one, using the relative atomic masses given in the table, in the periodic table, calculate the relative molecular masses of the following compounds. Now, the first one is ammonia. So, what is the relative atomic mass of nitrogen? It is 14, and hydrogen is 1. But how many hydrogens have I got? 3. All right. So I have got a total of 17. The relative atomic mass does not have units. Okay. The next one is carbon dioxide, so CO2. Well, carbon has a mass of 12, and oxygen has a mass of 16. But how many carbons are there? Well, 2 of them. So in total, I have a mass of 44. Yeah, bye. Joshua, did you do them? Okay. The next one, copper sulfate. CuSO4. The mass of copper, 64. What's copper? Yeah, 63, but we can round it off to 64. I think your tables have 64. 64. Sulfur is 32, and oxygen is 16, but how many oxygens are there? We have 4 oxygens. So the total mass, 192. And lastly, we had glucose, a sugar molecule. Oh, did you only do up till C? All right, let's do glucose, C6H12O6. Well, it is going to be 6 times carbon is 12 plus 12 times hydrogen is 1 plus 6 times oxygen, which is 16. Did any of you work it out? That one? 180 for the relative atomic mass. All right. Okay. Now we have to carry on with the periodic table. And then just very simply, people, the structure of the periodic table, we have horizontal periods and vertical groups. Okay. In general, we refer to 8 groups All right, we ignore those transition metals in the middle. We don't put them into a specific group. And then the periods are the first two elements, hydrogen and helium, lie in the first period. Then lithium, beryllium, boron, neon lie in the second period, etc. Okay? In general, the elements in the different groups are grouped together because their properties are more or less the same. Now, the first thing that we must have a look at in terms of the different elements on the periodic table, the old exercise, you did it in grade 8 for the first time, where we're going to have a look at the electron distribution. Hydrogen has 1 electron. Right over here, next element there, helium has got 2 electrons. Yeah, you've done it. Lithium has got 3 electrons. All right. Beryllium has got 4 electrons. All right. Boron has got 5 electrons. All right, and so on. What is the pattern that we get? Can you remember?
Those 2 shells in the periods and in the second period.
1, 2, 3, 4, 5, 6. Oh, I've only got 7. I need another one. 8. All right? Let's just quickly do underneath lithium, we get sodium. How many electrons does sodium have? 11. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What is the pattern that we get?
Is die periods wat die nommer van die periode is hoeveel shells?
Yes. The period number tells me how many shells there is. The group number tells me number of electrons in the outer shell. All right? So all the group 1 elements will have 1 electron. Group 2 will have 2 electrons in the outer shell. Group 3 will have 3 electrons in the outer shell. Group 4 will have 4, 5, 6, 7, and these will have either 2 or 8. We say it has a full outer shell. Remember, the first shell can only take 2 electrons. All right, so 2, 8, 8, 8, 8. Yes, we will come to the SPD notation in a moment. You must just first be with it on this. Okay. The number of shells, people, is important because the electrons, the elements, when they form bonds, it is the outer shell electrons that are involved in chemical bonds, not the inner ones. Okay? The inner shell electrons don't have enough energy. They are held close to the nucleus. The outer shell electrons are shielded from the nucleus, and it's easier for them to be lost or gained or shared. All right? So chemical bonding occurs on the outer shell electrons. The shape of the periodic table tells us how many electrons in which shell. If I go and say to you an element like, okay, let's take selenium. Selenium lies in 1, 2, 3, the 4th period, and it lies in group 6. So selenium is going to have 4 shells, and the outer shell will contain 6 electrons. Do you understand? Okay. Now the transition metals, they form on that periodic table the green group. Now they sometimes can differ, we say, in terms of oxidation states. Remember, metals, when they form ions, they tend to lose electrons. Now we find that they sometimes can lose 1 electron, sometimes they lose 2, sometimes they lose 3, and sometimes they can even lose 4. Which means, for example, if I look at something like iron, I can get the compound iron chloride, and I can get another compound iron chloride. And they are chemically different from each other for the simple reason this iron makes 3 bonds. So it has 3 bonding places. That iron makes 2 bonds, so it has 2 bonding places. In other words, if I broke up the ions, that one is iron 3+, and that one is iron 2. So how do you know if I say, I've got iron chloride? Yes. We have to, in brackets, put in a Roman numeral 1 or 2. So the name must be iron. Oh, sorry, not 1, but 3 or 2. Iron 3 chloride. Yeah, because this 3 refers to the iron. It's got 3 bonding places. So I have iron and I have chlorine. This iron has 3 bonding places. Chlorine only has 1. So I have 1 of them, but 3 of them. All right. If I get a formula, copper 2 chloride. Copper has got 2 bonding places. If I have copper 1 chloride, it's got 1 bonding place. So copper 2 chloride would look like that. Eh? And copper 1 chloride would look like that. Do you understand? All right. Okay. So the terminology is they have more than one oxidation state. Now, oxidation state you will do when you get into grade 12. But just take note, the transition metals can sometimes have different amounts of bonding places. It depends on what it's reacting with, how much energy is available, etc., what product will be formed. Okay. Right, now, the next section, there on page 25, the heading says, Higher Studies. And seeing as you are all busy with higher studies, you all have to know what I'm doing. Now, when we worked with atoms, we have the nucleus, all right, with the protons and the neutrons, and then in shells around the nucleus, we get the electrons. Okay, now, if I could cut it open like that, then, first shell, second shell, third shell. Are you still with me? Fourth shell. Now, the first shell can take 2 electrons. The second shell can take 8. Okay, and I'll just stop there for a moment. Now, electrons tend to form pairs. How does it work? Because electrons are negative, they should actually repel. But as the electrons are moving around the nucleus in an orbit, they are also spinning on their own axis. Electrons with opposite spin will attract, yes. And that's how they pair off. Electrons with the same spin repel. All right, so we find that within these energy levels, electrons tend to form pairs. But what they're going to do is they first put one into position, and then the next one will come in, because it's also got to do with the energy state of the electrons. So, into the first shell goes the electrons with the least energy available, and it goes into an orbit which we call an S sublevel, and we represent the electrons with half arrows. That would imply I have electrons with opposite spin.
It's like 3 electrons.
Yes. So the first energy level has a so-called S sublevel. The second energy level, the second shell, has got two sublevels. An S sublevel and a P sublevel. Now these sublevels, it's got to do with the shape of the path the electrons follow when they go whizzing around the nucleus. Okay? The S sublevel is just circular. Okay, so it's in a circular shell. The P sublevels, there are actually 3 of them, and they look like this. And then into the board and out of the board, X, Y, and Z planes. And in each one of those shapes, 2 electrons can go. Now you don't need to know about the orbital shape. That's not part of your syllabus. Yes, because in the second energy level, the electrons travel firstly in an S sublevel, all right? And then we will have 3 Ps. P sublevels that divert 90 degrees to each other in 3 dimensions. All right? So what they are going to do first is, one will go into the one will go into the other, one will go into the next. If I am representing, let's say, element, let's say fluorine. How many electrons does fluorine have? 9 electrons. So 1, 2, 3, 4, 5, 6, 7, and now they will pair off 8, 9. How many bonding places does fluorine have? 1. Yes. All right? If I had a look at something like nitrogen, nitrogen has 7 electrons. 1, 2, 3, 4, 5, 6, 7. How many bonding places does nitrogen have? 3. Do you understand? All right. Okay, so now in the third sublevel, and this is where it deviates from our model of 28888. But if you remember correctly, we would only work with the first 20 elements. Because this model of 28888 only works with the first 20 elements. Because up to here, I will now have 10, 2, 4, 6, 8, 10 electrons. Now the next one is 3 Ps and 5 Ds, and that would be an S. So SPD sublevel. And the D sublevel just has a different shape to what the P and the S sublevels have. You don't need to worry about the shapes. Yeah, small letters. Let's say element number 20 is calcium. So calcium is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now it jumps that one, 19, 20. Because the picture of this is, there's our first subcell. This one is superimposed over that one, and that one is superimposed over the previous one, and what it comes down to is it requires less energy to fill an S sublevel than it does to the D. So calcium with 20 elements, 20 electrons, has 2 electrons in its outer shell. It fits the pattern perfectly.
Okay, so you reach P sublevel van die tweede een.
Yes.
Is onder die P sublevel van die derde een.
The energy level, yes. After that one, you go to that one. Okay. If I went on, gaan nou vir jou ene wys. Let's take selenium. It's got 34 electrons. 2, 4, 6, 8, 10. Are you with me? 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. No, it drops back to the D. It just does because it's got to do with the energies. Okay?
But don't you need more energy to fill up the D than you need?
No. Those on the outside have more energy. Those on the inside are pulled close because they've got too little energy. All right, it works back to front. Now, it becomes even more complicated than this because then in the fourth subshell we have SPD. So here we have D sublevels and then 7, 1, 2, 3, 4, 5, 6, 7 F sublevels. Okay. Now we won't even... It doesn't matter. It's just, you just fill them up and there's a specific order. And I'll show you a pattern how to know the order because now it starts jumping. Okay? But they don't normally ask further than this. I'll show you. I'll show you now in a moment. Okay? Yes. I'll show you. All right. But do you understand about the distribution of the electrons? Okay. Now, before I go any further, when I look at the periodic table, it's actually quite spectacular. You can also divide up this periodic table into S, P, D, and F block elements. It means the S block elements have their outer shell electrons in an S sublevel. This one will have 2 electrons in the 1, 2, 3, 4, 5th shell, the S sublevel. Okay? These are S block elements. These are P block elements. Remember, we don't work with them. Okay? P block elements. They have got electrons that are unpaired in the P sublevel. So that is where their bonding will occur. Whether it's in the first, second, third, or the second, third, fourth, fifth, sixth, seventh shell, it doesn't matter, but their electrons, their outer shell electrons will lie in the P sublevel. These are D block elements. So their electrons will lie in the D shell or subshell. F. Okay. So we have S, P, D, and F block elements. Yes. Yes. That is why they are there. Okay. There's a very specific reason for the shape of that periodic table. Yeah. Yes. 10 electrons will go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got a filled outer shell. Ja. Ja. No, they will always go. They will always go in from the bottom to the top in a specific order. Wacht, waar is jy nou? By this? There. But this P sublevel consists of 1 S and 3 Ps. So there is place for 4 pairs. Verstaan jy? In total, I have 8 electrons there. I have, in total, 2 electrons there. Yes, the first one is close to the nucleus. The next one is slightly